Good afternoon, and it is afternoon. It's no longer late at night. I'm no longer tired. It's no longer even the same day, and so I'm ready to go. So, and where we left off in the last recording is I'd gone through a discussion of how the pardon me, how the thermal energy is related to the temperature of a isolated system. And, well, I shouldn't say isolated because I'll allow the possibility for things to flow in and out, typically energy to flow in and out, because if so, the energy, the thermal energy will change, so delta E sub TH will change, and as a corresponding effect, the temperature will change. In any case, I pointed out that the change in, sorry, the lights did something weird in here. Pardon me. Anyway, the change in thermal energy was related to the change of temperature, and also to how much of the substance you have, how many particles you have, and then I started talking about it in terms of mole, in terms of moles, how many moles of the substance you have, and so I mentioned Avogadro's number and Avogadro's constant, which are related but different things. Avogadro's number is simply a number, 6.022 times 10 to the 23rd particle, well, 10 to the 23rd, no units. And then Avogadro's constant is the same number, 6.022 times 10 to the 23rd particles per mole. And so the mole then is defined as an amount of substance. And so the relationship was that the thermal energy, so we'll go with the thermal energy at a fixed temperature rather than worrying about a change of temperature, at least yet. So the thermal energy can be calculated, well, one way to do it was by multiplying the number of moles you have of a substance times Avogadro's constant, pardon me, times Boltzmann's constant also, and then multiplied by the temperature that your system happens to be at. And I then said, okay, well, since I know that Avogadro's constant is a constant, the Boltzmann constant is a constant, then their product is necessarily a constant. And so if I define the letter R to be simply the product of these two constants, R itself is obviously constant, and plugging in the given values of those two things, we got 8.31, and then we have, let's see, Avogadro's constant has units of 1 over moles, and Boltzmann's constant has units of joules over kelvins, and so that's the unit of R in the SI system. And that allowed me to then write that the thermal energy, sorry, there was a factor of 3/2 here, that the thermal energy was 3/2 nRT. Great, great, great. And as I pointed out, this shifts the responsibility on you from knowing how many particles you have to instead figuring out how many moles of substance you have. And as I also pointed out, that's typically easier to do than counting the number of, a vast number of particles, which nobody ever does. It's always in moles. So this should be straightforward, but in any case, sorry, I just had something eaten and it's caught in my throat. This bit here, I said at the end of the last recording, might look familiar to you, and in fact it is, that stuff that I've just underlined in purple is the right-hand side of a relationship known as the ideal gas law. You're probably familiar with it, but I'm not going to assume you are. I'm going to write it down and I'm going to talk about it a bit. And so let's see where we are. Essentially, the idea is this. Well, as we always do in physics, we would like to be able to ask and answer questions about whatever physical system we happen to be investigating, whether it's a pen that we drop and ask how long does it take to hit the floor, how fast is it going when it hits the floor, how much does its potential energy change, or whatever, so that's our system under consideration. On the other hand, we might wonder about if I have a container full of gas, if it's at a given temperature, what does that say about its pressure? What does that say about its volume, and how are those things related to each other? And for that matter, how are those things related to how many moles of substance we have at that temperature? So there's a lot of questions we could ask, and the ideal gas law is a relationship that relates all of those things that I just rattled off and allows you to answer those kind of questions. I'll write down the expression, and then I'll point out a couple of things. EV equals nRT. Okay. Point out, so here's some things to point out. First of all, there's no 3 halves here, so that tells us we have to look at something. Then too, N, R, and T we've talked about, but P and V we have not yet talked about. Now, you probably have a reasonably good idea of what those are, but I better not assume that. In any case, I have my own things I want to say about them. This object now is not a container of gas. It is a container of liquid, however, and many of the same rules apply to a container of liquid as to a container of gas. Certainly the concepts of pressure and volume do. Volume, I don't think I have to labor the point too much about. It's the number of cubic meters in the interior contained by this object. Okay, and this one even tells us. Let's see, this thing has a volume of there we are, 500 milliliters, which you can convert that to cubic meters if you wanted to, which I don't particularly right now. And then pressure. This thing doesn't list the pressure, of course, because it can't. What's pressure? So volume is okay. I probably don't need to labor that one. But pressure, let's think about this. I have this, you draw it. I want you to feel that I'm using a real physical system, not just making something up. Over here. Fabulous. All right. Now, this thing, as I say, is filled with water instead of air, but the principles don't really change. There's a couple of things, and by the way, I am now going to simply magnify this drawing. Now that you know that it's something real, I'm going to make it bigger just so you can see what I'm going to draw. Hopefully keeping the proportions more or less the same. All right. Terrible top, though. I wonder if I can do better. Not too bad. Okay, good enough. So it's filled more or less to here. Now, from this point forward, I'm going to pretend that it's filled with air instead of water. I will avoid anything that is specifically tailored to water, or at least if I do run across it, I will make a point of telling you what I've got. Okay, so filled with air now, right? Now, our air molecules are bouncing all around. We've talked about that, and the higher temperature the gas is at, the faster they're moving around. Remember, that's what thermal energy is. It's a measure of the average kinetic energy of the particles of gas inside our container. So the higher the temperature, the faster these particles are moving. But the particles, as they move, of course, they collide with each other, and we've talked about that. But in addition to colliding with each other, the particles will also collide with the plastic, right, with the boundaries of our volume. And when they do, like during any collision, any change of momentum, there's going to be a force exerted. In this case, every time a particle of air hits the side of the surface moving that direction, it will exert an outward force on the plastic container, on the plastic bottle there. And so the force will push outward, okay? And then the colliding particle will, of course, bounce back the opposite direction. And the same thing happens over here. A particle of air hits the plastic this way, pushes out this way, and bounces back the other way. But they can also move up and down just as well. And so this is the top layer of the water. If it was air, it would fill all the way up to the top of the cap here. But the water can move downward just as well as the air molecules can move downward just as well as they can move left and right. And for that matter, they move forward and back. In short, in this bottle of water or an equivalent bottle of air, okay, look at that, that's pretty good. The particles are continuously colliding with the surface here, pushing outward away from the interior of the volume in all directions. And I could do that. I could flip it over, and now they're colliding with the cap. Okay. The bottom line is that at every moment, there are countless numbers of collisions of particles that are pushing outward in every direction on the plastic bottle. Okay. And the consequence of that, the consequence of that is that all of these outward forces applied over the entire surface area of the of the bottle is keeping the walls of the plastic bottle stiff, rigid. There is, like with kinetic energy, and for the same reason, there's no hope whatever of determining all of those forces individually, and we don't try. So instead we do, again, kind of an averaging process, but what we do now is we average all of the forces acting over all of the interior surface area of the bottle, and so we have forces, 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 so on and so on, forces, 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 over the entire surface. I'm not going to draw all these gazillions of them. Forces down, forces down, forces down, forces down. And then we say, okay, then there's these forces are being applied to this entire surface area, and that's what I'm drawing now. I'm emphasizing the surface area over which, or upon which, every one of these forces is acting. And so the concept that we define that does this averaging sort of process that I'm suggesting, this concept is called the pressure. Okay? And the pressure, then, is defined easily enough as the force that we apply, the force of each collision divided by the surface area over which that force is being applied. Okay? You can see that the units here are newtons per square meter, and this gives a special unit. This combination has a good name. This concept of pressure was first described by the French physicist Blaise Pascal, and so this unit is named in his honor. And it is one of those rare units that is actually made from two letters. And so it's P, capital P, lowercase a, and it is defined to be a Newton divided by a square meter. Again, it is a unit in the SI system. All right. As you can see, if you either change the surface area over which the gas is, upon which the gas is acting, which is unlikely, or more typically, if you change the force of the gas particles, hitting the sides of the surface, then you will automatically change the pressure. You almost never change the surface area of your container, but you very commonly change the force. And it's easy to change the force of the collisions here. All you have to do is heat the gas up. Because why? You heat the gas up, the particles move faster. That's what higher temperature means, is the higher kinetic energy, higher average kinetic energy per particle. Well, if the particles are moving faster, that means they have more momentum when they collide with the sides of the surface. Bigger momentum, bigger change of momentum, bigger force. Okay? So in short, the way to increase the pressure is to increase the temperature of the gas. And you can do that by artificially adding energy. Okay? Lots of different ways to do that, of course. Boil a pot of water or something. Or heat up the gas, or cool it down. Take a bottle of air and put it in the freezer, and it'll cool down, and the molecules of air will move more slowly, hitting the sides of the container less, and the internal pressure will therefore drop. Okay, so that's the relationship then. One last comment before I end this recording, and that is the name here. It is ideal gas law. This relationship here, for technical reasons, only holds true for a so-called ideal gas, and I talked about briefly an ideal gas in a previous lecture, which is essentially that there's several properties of an ideal gas, but the big one is that the particles, as they fly around the container, interact with each other only by direct collision with other particles. Okay, there are no long-range forces. We don't have to worry about electrical forces or gravitational forces or any other kinds of forces, except the force that happens during the collision. Okay, if that is not true, and for for many gases that assumption isn't true. To the extent that it isn't true, this relationship is not completely correct. However, it's surprisingly a good approximation for most gases, ideal or not. Okay, and so it's certainly a good starting value for any calculations that you might want to do. One last comment. I'm not going to use them particularly much, but you should know that there are other units of pressure that are in common use. There's millimeters of mercury, which is a bizarre unit. It comes from the history of the development of the science of gases, and its most familiar use these days is when you get your blood pressure taken at the doctor's office. The numbers 120/70 or whatever your blood pressure happens to be, those numbers have units of millimeters of mercury. Why that bizarre unit? We'll talk about it in class. Another one is the atmosphere, which is abbreviated ATM. And these are not part of the SI system, by the way. And so the atmosphere is essentially the pressure that the atmosphere applies on you and to you. Okay? And that turns out to be surprisingly high in the U.S. system of units, which is the one I just happen to remember, let's see, it's, well, no, actually, I do remember. 1 atmosphere in pascals is 101.3 times 10 to the 3 pascals. And in the U.S. system of pressure, that's about 14.7 pounds per square inch. So that might give you I'll say 1 atmosphere. That might give you a sense of the pressure that atmosphere puts on you. And a common question is, really, I have this much pressure on every square inch of my skin? The answer is absolutely you do. Yep, the air around you is putting this much pressure on you. Why don't you crumple up like a little balloon? Because your internal pressure is about the same as this, and that outward pressure from your blood and your organs and the various bits and pieces inside your skin, they push outward with the same force per unit area. As the air is pushing inward on you and the two pressures balance, no net pressure, no net force, you don't feel anything. And why does that happen? How does that magically happen? Because we evolved in this atmosphere, and our bodies are evolved to do that automatically. Okay, so that's that. Okay. So with those assumptions, then those ideas, this is the ideal gas law, and in the next recording, let's talk about what sort of things happen to the gas when you change the various parameters in this expression.